We are looking at the steady state flow of heat without heat generation in more than one dimension. And essentially, we will be focusing on the two-dimensional domains. Let's start by the general heat conduction equation in a Cartesian domain. So if you recall, this general form of heat conduction was resulted from the balance of energy from reduction of that part. So we have x. This is the heat flux in minus out in the x direction. The same thing, in minus out the y direction. The right hand side shows the storage or the accumulation term, which we are in the steady state. So this is going to be 0. Have steady state condition. Let's assume no generation, no heat generation in the system. So this term will be 0. And let's look at the 2D dimensions, okay? So we are essentially looking at the 2D dimension, x and y. Now, if we assume constant k, then we would have kx equal to ky equal to k. And from here, we can simplify the top equation to second order PDE. And that's what we refer as a Laplace equation. If I want to represent the heat transfer in a 2D domain, I can show it by on a solid. Let's say we have a solid with this geometry. And this solid could have, like, it has actually a depth in the z direction normal to the surface, but let's assume this is x direction and this is y direction. And further assuming these two surfaces are adiabatic or insulated, so we have insulated surfaces at the top and bottom. If by somehow you know the temperature profile inside that and you want to plot it, and let's assume this is T1, so the left surface is T1, the right surface is at a lower temperature, let's say T2, okay? So T1 could be, T2 could be, I don't know, 25 degrees C, and T1 could be, let's say 100 degrees C. Now, when you find the temperature distribution inside this solid, what you're gonna see here is these are the lines that are showing the points that have the same temperature, or we call them isotherm, okay? So these lines constant temperature, or we call them isotherm or isothermal lines. This is another name for them. What happens here, you would see like these points are kind of sketching and then changing in time. Now, we know by heat conduction equation, what we have here is, if I want to find out the heat flux, let's say q double prime x is going to be minus k dt over dx, and q double prime 1 is going to be minus k dt dy. So at any point in this domain, if I find out what is the temperature gradient with respect to x and y, I can find the flux, and always the heat flux is going to be normal to this isotherm. So let's say if I'm going to find at this point what is the heat flow, the vector is going to be always normal to that. So this is going to give me the vector q double prime or q, and if I just want to exaggerate that one here, so let's say you have this surface and it's going to be q double prime. This is going to be always normal to that, and it has two components, q double prime x and q double prime y, that we can find from here. Along the isotherms, since they are at the constant temperature, let's assume, for example, this is, let's say 100. Let's assume this is 90. This is 85. Like all these points along these lines are 85. Let's say this is 80, 75, and so on. That's going, since the temperature are the same, the gradient is going to be 0. So what I can say about this picture here is, long isotherms, there is no heat flow. Since dt, let's say it shows by, we show this curvature by s, dt ds is 0. Or this line by s, dt ds is going to be 0. So always along the isotherm, we don't have any flow. Okay, so that's one thing. And whenever we have a flow, like heat flow, is going to be perpendicular to this isotherm line. So heat flow vector is always, you can show it by this sign of the perpendicular or normal to isotherm lines. We call them here line, but if you look at the depths, they're all like a surface. So these are isotherm surfaces. I'm just going to add it here. This is the second characteristics. Now, what we do here, or our aim here, is to solve this Laplace equation to find out this temperature distribution. Or in other hand, when we have this temperature distribution, we can find out what is the heat flow rate in this 2D domain. So we solve that Laplace equation, which is for 2D steady state and no heat generation, to obtain temperature distribution. And okay, we solve this equation, which is for 2D here, steady state, no heat generation, to find temperature distribution. This is 2D, so it's going to be T, X, and Y. And from here, we can get Qx and Qy, the heat flow rate. The other part related to that is this Laplace equation is a second order PDE. So we need boundary condition. This equation is a second order we need two boundary conditions in each direction. So what, two in x direction, and we need two boundary conditions in the y direction to solve this PDE. Now, the way that we solve it, how to solve Laplace equation. As a reminder, how to solve that? There are various strategies or methodology to solve that. The first and the best one is analytically. So we can solve it analytically. It has advantage and disadvantage. The first advantage is the analytical solution. First of all, it provides an exact solution, and most often exact closed form solution. And it gives, when we solve that one, it gives temperature at any point in the domain of interest. So at any point of solid, in fact, temperature T is a continuous function of x and y. So when we solve, let's say for this domain, if we can solve the Laplace equation with the boundary conditions that we have, what we are gonna get here is the temperature at any point that you select here. So it's gonna be continuous function of the x and y. However, it is limited to well-defined geometries and boundary conditions. So in terms of the solid, the domain of interest, we should have a very well-defined geometry, and we can find for very well-defined geometry and for specific boundary conditions and analytical solutions. Another way to solve this Laplace equation is by numerical methods. So we can solve it numerically. It has, again, its own advantage, disadvantage. One of the things here is it provides an approximate solution. It is an approximate solution at discrete point. So the way to deal numerically is the domain of interest that we have, we start to discretize that domain and define nodes and find the temperature on each of these nodes. But we, we tend to increase the number of nodes so we can get as better estimate as possible. And the advantage here is, in fact, it provides accurate results for complex 2D or 3D or 3D geometries with various boundary conditions. So unlike the analytical solutions that is very limited to very well-defined geometries and specific boundary conditions, with numerical methods, we can solve almost for any geometry and any type of boundary conditions. So that's the advantage of numerical solution of this Laplace equation. The other one is graphically. And graphically is the same way that I was showing here, that let's say we have this domain, we find the isotherm lines with the well spacing, and then besides these isotherm lines, then we have the heat flow that are going to be normal to them. So this is, if I want to plot that one, it's going to be normal to that one. This is a no heat flow. And then we find, always is going to be normal to them. We find this, the vector, like heat flow vectors and isotherms, and based on them, we can develop some graphical method to estimate the heat flow rate. And it's a very quick and quick estimate of, I would say, like heat flow. So it provides a quick estimate of heat flow rate.